All right, welcome back, everyone. We have Sia Ghelichkhan taking over from Rhodri Davies, and Sia is a lecturer in numerical geophysics at the Australian National University.
Beautiful. Yes. Oh, this is going to be weird, just looking here. All right. Hello, everyone. I'm filling in for Rhodri Davies, so you're going to see a lot of me today. Yeah, I'm basically filling in Rhodri Davies and the entire Geodynamics team. So this is going to be more or less an introductory talk about the Geodynamics project, and I'm basically representing this amazing team. And most of these people are sitting in the audience. Now I'm going to start by showing these three different Earth processes, and an overarching goal of Earth sciences is basically understanding past and future evolution in each of these cases. We have heard about deep mantle contribution surface processes today. We heard a lot about GIA and sea level prediction, and also groundwater modeling. Now, our response to this quest to understand these processes has been to collect data. And these are some of the efforts supported by AuScope for the years. Obviously, it could be way more about all the AuScope supported endeavors over the years. For example, AuSLAMP and all these different seismic arrays, where amazing science has come out of that about imaging the interior of the Earth and snapshots of the Earth at present day. I wish I knew about what Matt is going to present. There has been lots of effort in monitoring vertical land motion and measuring sea level change, which is very essential for the resilience in building resilience in Australia and Pacific nations, which is again partially supported by AuScope, but also by federal investment. We send our best scientists to Antarctica, to the worst places, although Anya insists that it's a very amazing place to be. But again, to collect data about Antarctica, about ice sheets, about the interior of Antarctica, just to know what is going to happen, what is going to be the effect on sea level change. And the same thing can be said for groundwater. We have these repositories of bore data, of hydraulic head measurements over the years. Now, it sounds like we're collecting a lot of data, and this is a necessity. We should do that. However, I want to use my favorite quote that it seems like we are drowning in data and starving for wisdom. Now, I know there's a lot of data people here. What I'm claiming is not that we have enough data, is that where would be the best added value to all this data? Where can we convert these images, these snapshots, into understanding of how the past has been and how the future is going to turn out? And for that, what we typically do, we turn to models. We try to use these physical principles that connect different conservation laws to each other. In case of mantle convection, there has been decades of developing models and basically trying to understand models. And these models have basically gone more and more sophisticated with different capabilities in them. A major shortcoming that is always mentioned when it comes to models is that they are not necessarily attached to data. They could be just completely detached from what has happened for the Earth or the Earth system processes. And this typically can be shown by this diagram that imagine the blue line is the Earth mantle or any other Earth process, and what the model predicts could be completely detached. It could start from somewhere else. The physical laws are consistent, however, because of the parameters being different, they are not necessarily telling us anything about the Earth. Now, in response to that, what we can do, we can turn into, this is the issue with these, we can turn into data-driven inverse approaches. And an approach that has been more and more used is optimization techniques, which basically using the data and learning from the data in order to optimize models, in order to optimize the parameters in these models so that we can reproduce the Earth system processes. And this has been used for weather forecasting techniques for decades. But one of the major challenges with them is the fact that they are notoriously difficult to develop. The math is very hard. Usually they are developed for a certain realm of geosciences, but it's very hard to transition them over all the other disciplines. And here is where Geodynamics comes in. It's a platform specially focused on data-driven modeling using adjoint techniques. This is where the name comes from, is a geoscientific adjoint optimization platform. Adjoint optimization is a technique used to learn from data and to train these models and optimize these models. Initially supported by AIDC and now very proudly and kindly supported by AuScope for the past few years. Now, the idea, this is a few years old, this graph by now. The idea starts with this opportunity that we have all these data that is collected from depth of the Earth at the surface, and we have developed all these computational infrastructure in order to model these processes, but they are usually in separate realms. They're not really talking to each other. Use that as an opportunity and couple these models together to learn from the data and build the so-called digital twins for different Earth processes, for example, mantle, GIA, sea level modeling, in order to fuse data with models and have these predictive power for these different processes. What is Geodynamics in depth? It's a forward modeling and optimization platform. It has certain components. First of all, it's open source. Whatever we do is on our GitHub, and it's always published. It is always adjoint capable. Whatever we do is having a focus on data assimilation and how we can learn from this data. We will have two talks, one by me, one by Will Scott today, about the two approaches, for example, for GIA, and the other one is for the Earth mantle. There are different components. The main component is this software called Phaedric, and where we do the forward approximation solvers. It comes with automatic adjoint and optimization algorithms, and there are lots of capabilities that we are basically adding to as we go. And a core principle for us is that whatever we do should be fair, compliant. It should be findable, accessible, interoperable, and reusable. So instead of just repeating that, what I want to mention here is that a very core component of Geodynamics is the adopt part. It's not just an acronym. We want to adopt softwares that are out there. We're not reinventing the wheel for any of these parts. What we are going to do is we are relying on softwares that are developed by hundreds of software engineers and mathematicians, and we're leveraging $1 million of investment from different organizations. And it's a lot of work every week. It's not a week that we don't have a crisis because something has been implemented in one of these softwares and we need to move forward with them. But it is certainly worth it because of all the benefits that we can get from that. Again, we have four core principles. First of all, we need to achieve accurate, efficient, flexible, and easily extensible modeling frameworks for mantle convection, for GIA and groundwater, as we will discuss. And the core principle is that through this connectivity, through Dolphin Adjoint, which is a well-known numerical software, we are able to provide optimization capabilities. And one of the things that motivates us is our interdisciplinary approach. We try to do modeling across disciplines in order to use the data that is being used across disciplines in order for all these different Earth processes to talk to each other. And we are moving towards fair models that can be accessible through what we're going to hear, for example, the MATE project and other projects for all the earth scientists for digital twins that can be accessible. We have published 2 papers so far about the fundamentals of GeoDop, so we've introduced the project. We've recently published the Glacial Isostatic adjustment component of GeoDop. We'll be talking more about that. So this is part that we're basically showing Tim that we are actually delivering on what we promised. Please be happy with us. So basically what we have achieved recently, the most complex formulations of Stokes and viscoelastic energy in free surface for Earth mantle. We will soon have groundwater components of GeoDopt, where, for example, we can ask the question, given this data for bore data or these gravity changes, what are the parameters of the different aquifers that need to be adjusted such that we can fit this data? Complex rheologies for, in case of sea level modeling, this is going to be a unique opportunity for scientists to ask questions that would have not been possible so far to answer because the infrastructure was not there, and we're already working across Australia and internationally to look into some of the data that has been collected for Antarctica and elsewhere on the planet. The great work by Thomas in developing multi-material features in GeoDopt, and also as software engineers that have worked hard to connect GeoDopt to other AuScope supported softwares, for example, Gplates. And instead of just producing all this data that lies somewhere around and we need to read through I/O, we are directly linking to all these other softwares to basically cut these middle steps for everything to be fair. So every data is easy to access and easily imported into GeoDopt. We have added mesh adaptivity, which was one of the things that we have promised to AuScope, and we just recently delivered our new features for temporal discretization in GeoDopt. I will talk more about the Earth mantle digital twins, so I will not talk about that, but again, adjoint-based inversion, which is the optimization part, is a core component of GeoDopt for every process that we'll touch on. These are some of the results for our groundwater modeling. We're very excited to have groundwater as a core modules of GeoDopt. So on the left, these are 2 equations that are notoriously very difficult to solve because of the nonlinearities. And we have examples that shows how well we're solving them within GeoDopt. This is an example of meshing the lower Murrumbidgee Basin, and we are just simulating groundwater flow over a decade there. The exciting part is that we can do data-driven approaches where all the data that's been collected over the decades we can simulate, and we can produce these digital twins for different aquifer systems in Australia, which can be used for water budgeting and so on. This is a project supported by SmartSat CRC, and we're working with the Bureau of Meteorology as our stakeholders to see which directions we should go. Now, I will end with this slide about our website. We try to keep it updated as much as possible, so you can follow us and all the recent features. We had our workshop just 2 days ago. We try to keep it up every year in order to showcase our capabilities. So please be in touch. And yeah, thank you very much.
How good. We do have time for a question. Do we have any questions in the audience? No? Going once, going twice? Yes, at the back there.
Yeah, what are the biggest directions for developing this platform? What are the new features you're hoping to implement in the near future?
So far, we've been very heavy on development, so we haven't done research. One of the directions that we are going to do in the very imminent future next year is just basically doing actual science with collaborators across Australia and internationally to, for example, digital twins for Earth's mantle, or Will is leading a project with University of Tasmania, Matt King, on that aspect for some of the data that has been collected from Antarctica. Groundwater obviously will be something very exciting for us, and applying it to, for example, there's a project to look at some of the aquifers in the Murray-Darling Basin and see if we can come up with some budget estimate for how much subsurface flow has contributed to, for example, the droughts down the stream. One of the areas that we will, is actually one of the areas that we promised for some proposals and we're looking into is landscape simulations. For example, how erosion and tectonic forces can change the landscape over a million years. And that would, again, be looking into data that has been collected through AuScope efforts or GA to see how we can fit past topography and so on.
Thank you so much, Sia. So now we have Sara Polanco, who is a lecturer in the School of Environmental and Life Sciences at the Newcastle University. Let me get you set up. I'll give you the mic.
Great.
Scooch me this way. There we go. Take it away, Sara.
Okay, great. Okay, so is this not working?
You can use that. That is easier. Just make sure you come close to it. There we go.
Can everyone hear me? Yep, thank you. Yeah, so as it was mentioned before, I'm Sara Polanco, and I'm a lecturer at the University of Newcastle. And today I'm going to talk about a platform that we have created to distribute, share, and curate numerical models of Earth's systems. And so MATE is a collection that provides a wide range of computational models, their visualizations, inputs, codes, and their outputs. And so, yeah, MATE provides a digital platform that encapsulates the whole model development process. A lot of you in the audience are modelers, so you understand the challenges of encapsulating all that process into one single platform. And I also want to emphasize that MATE is built for the specific needs of the geosciences community. And so, but before I continue, I want to acknowledge all of the people and the teams and the collaborations that we have used to build MATE, and so a big shout out to AuScope for funding this opportunity, and to NCI and the Sydney Informatics Hub, and all the people who made this possible. So as you all know, the field of numerical modeling of Earth systems is rapidly growing, and the complexity of those models is increasing. And so I have this cartoon illustrating that, but again, you all know how complex these models are getting and how complex the workflows are getting. But our challenge is that they use specialized HPC, and then these models take days to weeks to run, and they produce a large volume of heterogeneous output data. So where do these models end up? So they end up with a DOI in an image, in a paper, in a PDF. Sometimes they end up in a hard drive. We are all guilty of it. Please raise your hand if you have models in your hard drive. And if lucky, they end up in a code. So the code ends up in GitHub or in Zenodo. But I want to remind you that both GitHub and Zenodo have a limited capacity, which is only tens to hundreds of gigabytes. But these model outputs can produce terabytes of data. So the challenges of managing and utilizing numerical models is that, for example, if we look only at the code, this study from 2020 looked at this, and so only 12% of those codes were in FAIR repositories. And so it's even worse for the output data. And so the community has recognized that there is a need to share these numerical models, but the issue is that there is a lack of community standards that hinders our ability to access, interpret and build on these published numerical models. And for example, the geochemistry community, we have seen, for example, Earth Bank, and many other communities do that, right? They publish the data, and then we can use the data, increase the impact of those outputs. And so why don't we do the same thing for the numerical community? And so, numerical modeling community. So yes, that was very well highlighted or written in this piece from AGU that is titled, "What is FAIR for Geodynamics?" And so also there's another publication here from the head of Figshare, which highlights that in a survey that was done, one of the challenges included the space limits on traditional repos, the lack of adequate metadata models, and then also cultural factors as to like, why do I have to share my model, which hopefully are changing. And so, but if we look at the data science community, they have this concept of data lakes, where they collect the data, then ingest it, blend it, transform it, and then they publish and then distribute the data. And then so that increases the impact because you have many users using the data for different applications. So based on this method or this approach, we decided to apply it to these numerical models. So we created MATE, which stands for Model Atlas of the Earth. And so it's a digital repository that encapsulates the entire model process, from setup to model output and analysis. And so it is also accessible to users with different models of expertise. But so the way it works is that the model gets submitted through GitHub. And so what I mean by model is more the metadata, right? So we capture all the metadata through GitHub. And then the actual data gets ingested into GeoNetwork. And so we have a entire collection in NCI, which is very exciting to be working with NCI on this. And so this generates DOI, and we can host large data sets. For example, we can host more than 1 terabyte of data for one single model. And then the other advantage is that the outputs are close to the compute resource. Then we have a visual interface, which is the model showcase. And so it's searchable, crawlable, and the content is automatically generated. So then that means that we don't have to have a software engineer or a web developer working full-time in ingesting the models. The other advantage is that, for example, if I am a lecturer and I just want to show beautiful videos or beautiful animations of subduction dynamics or delta evolution, I can go into a platform and showcase those models. So yeah, these are the 3 components. So that's the MATE trilogy, which is GitHub, the NCI collection, and then the static website that you can find in mate.science. And as I mentioned before, it has these beautiful summaries of the main takeaways of each of the simulations, which you can use on your lectures. And so then the model metadata is handled by AVRE crates. So AVRE crates is an open, community-driven, and lightweight approach to packaging research items along with their metadata in a machine-readable manner. And so it is great because, as I mentioned before, it's community-driven, and it has been created by researchers who really understand the challenges that we have across the board. And so it's based on schema.org annotations, but supports domain-specific vocabularies. And it also provides an integrated view over fragmented resources. And so now MATE is being showcased in AVRE crates. This is the AVRE crate website. And as you can see, we are also with our organizations or initiatives that are looking at workflows and digital twins, but also, for example, Language Data Commons Australia. So it's very exciting that MATE is now being showcased with AVRE crates. And AVRE crates are also being used by other disciplines. For example, such as the bioinformatics community that has large data sets of genomics data. So it's very exciting. And then again, like the really cool thing is that it integrates different parts and different components of workflows. And so this is, I guess, how it looks like. So we have all these references to what is called contextual entities. And so, for example, we have the DOIs, the ORCID IDs, the RORs for the organization, the software code, and the datasets. And we can bring all these links together in a bucket and then package it into a JSON LD. And then, as I mentioned before, what is really powerful is that it can point out to all of the different components of the modeling workflow. And yeah, so then we have this crate for each model, which is also linked to NCI through a DOI. And so the way the model submission works is we have automated workflows that are driven by GitHub Actions. And so we start with a GitHub issue template, where you, again, add all of the metadata. And then that triggers a series of events where we can create a new model, review the model, make changes if needed. And then that creates a model repository creation. And then we clone and configure that model repository and upload the model output to NCI. And again, that means DOI, so which is great because you can also have a DOI for your model. And so this is how it looks like. This is the how we capture the information. And so as you can see, this is an issue template created in GitHub. So it's great also because it is directly linked to your GitHub repository or your GitHub account. And so it has different questions. So it goes through the summary of the model code, the code and the output data, and then the software framework. And then this is where we capture all of the materials that you want to showcase in the website. So, for example, the beautiful animations and the beautiful images that you created are captured there, and then they can be showcased in the website. So yeah, this is how it looks like. Then we have one entry for each of the models, and then it's perfectly organized with a JSON here file that captures all of the metadata. And so, as you can see, this is how the website looks like. So it's beautiful because you can go through different tabs, and then you can look at the model setup, an abstract, and you can again showcase all of these numerical models in your lectures without being an expert, but understanding what are the boundary conditions and the main findings of your study. And this is how the model repository looks like in NCI. And so what's next? We are going to ingest some of the Geodopt models, so we are very excited about that, and it was great to have Sia giving the talk before me. And so we are also going to, we are looking for ways to collaborate with the computational infrastructure for Geodynamics. They have expressed interest on our platform, and also perhaps the possibility of mirroring some of the numerical models that they have stored elsewhere. And so also we are going to be releasing the outputs of Australia-wide groundwater modeling project that has been recently funded by the Opportunity Fund, and I'm also excited to discuss with Sia what the overlaps are or what the synergies are with Geodopt. But this Australia-wide ground model is going to be done in collaboration with Deltares, which is a company in the Netherlands, and that also will probably allow us to have links to EPOS NL. And so, yeah, if you want to learn more, please go to mate.science. Thank you.
We definitely have enough time for a couple of questions. Does anyone have any? Down here at the front.
Oh, sorry, maybe it's a silly question, but is there any sort of versioning control? Like if you upload a model, is it the end result, or will these get tweaked over time? Or?
Yes, so the idea is that this is going to be a gold standard, kind of like a Noah's Ark of models. But in saying that, we do want to have some benchmarks, for example. So we also think that it's important, for people to upload benchmarks, because we all know how much time we spend doing benchmarks, right? So, but yeah, it is a gold standard, a Noah's Ark of numerical models.
We've got one more question. Yep, in the middle. Thank you.
Great talk. I was wondering if there's any difference that you've seen so far for the way that you would have previously been publishing your models versus through mates. So increases in like reuse and adoption by others, or increased impact and things like that, or if it's maybe too early to see those.
It is too early to see those, but we do see that the fact that the computational infrastructure for geodynamics has contacted us to see if we can establish some collaborations as a showcase for the impact that we might have. But yes, I look forward to showcasing success examples in the future.
Thank you so much, Sara. Cool. So we've got our next speaker coming up with Jens. You around? Where are you? There you are. Hello. So we have Jens Klump, and I will just get your presentation up. I'll hand you the mic if you want the mic.
Thank you.
Here you go.
Yes, thank you.
Take it away.
Yeah, thanks everybody for being here this morning. I want to give you a brief overview of what's changing in the data access in the AuScope virtual research environment. And before I start, I do want to acknowledge the traditional owners of the lands that we all work on and pay my respects to the elders past and present. I usually work in Perth on the lands of the Whadjuk people of the Noongar Nation. Tim yesterday spoke about the downward-looking telescope and reminded us of this metaphor which we might use to describe what AuScope does, because infrastructure sounds so dry, and I think AVRE as a data infrastructure sounds even drier than many of the exciting projects we've heard about in the 1.5 days so far. And what the role is of AVRE in this downward-looking telescope is described as contributing to the data lens that brings all the information that comes from AuScope systems together and makes it accessible, firstly findable, but then also accessible for further work and analysis. And actually, AuScope Virtual Research Environments has been around for a very long time. It started out as AuScope Grid, if anybody still remembers grid as a term. Started in 2008, and at the time, the situation we were facing was that only the government geological surveys were capable of delivering data and metadata through web services. Web services were also a new thing. And AuScope Grid at that time played an important part in developing the technology stack that was needed to actually serve and share data through web services. The Spatial Information Services stack was a groundbreaking stack of technology that was adopted by a number of Australian government institutions and also internationally. And it's still the key access point to the National Virtual Core Library. But what we could also see that is, over time, the digital capabilities of other parts of the geosciences community outside of the geological surveys matured. And then also a big advancement came through the publication of the FAIR Data Guidance Principles in 2016 that really set a new standard for data infrastructures and for the way that we deal with data. And as an example that illustrates those changes is the Virtual Geophysics Laboratory, VGL, that was initially built to enable the processing of geophysical data on high-performance compute infrastructure for all geoscientists in Australia. And in that, it was very successful. Where it wasn't successful in the long run was that it only offered a limited set of data with a limited set of tools, and the authorization process to run it on different HPC infrastructures was quite difficult. So that didn't kind of then ask the question, why do we run this? Why don't we just run all permutations of data and code and store it on cheap storage and stuff, maintaining an expensive infrastructure? And in the end, VGL was superseded by new services on NCI and on the Easy Hub. So eventually we shut VGL down because it was no longer needed. The community had moved on. But we also built a number of other digital tools that helped with either finding information about infrastructure that is available or helped with analyzing and visualizing data that came from AuScope projects and programs. So in a little while back, we took some time to analyze what had evolved and what the needs of the community were, and conducted quite a number of interviews with stakeholders in the AuScope community and adjacent communities to find out where is the community in terms of their data needs and their digital capabilities, and where should we go next. And that then led us to rewrite our strategy and redefine our goals in having quite a number of discussions with AuScope headquarters to also find out what AuScope would like to see us doing. And so in this combination of the digital evolution, FAIR principles, we pivoted our offerings to include new aspects. So it's even more about improving access to AuScope-funded research data, but also providing services that strengthen the linkages between researchers, projects, and data sets, building relationships with academia and awareness of the AVRE through the build program. So we send out a call for projects every 6 months to call for projects. And even though this is just a short line, custodianship of AuScope-funded data, that's actually what would be called a paradigm shift, because in the first decade of AuScope virtual research environments, we never held data if we could avoid it. But then with the fair data guidance principles and emerging new needs in the community, we added this component of actually now becoming custodians of AuScope-funded data. But also what's important to know is that with the system that has been running for almost 20 years, there has been a number of changes, because as I already spoke about the user requirements that change over time, but then there's also the technology changes. In digital technologies, you can basically rewrite everything every 5 years. And so in 20 years, that's kind of 4 rewrites of the entire system. Even if you do, you still accumulate technical debt because there's so much change happening under the hood. If you don't keep up with that, things become brittle and eventually unsafe. So this requires us to think about what features are central to AVRE and which need to be added and which are no longer used. So we use user analytics on an abstract level, not on an individual user level, to find out what are people actually using. And interoperability has always been an important part of AVRE, starting with the state geological surveys and their data sets, but now with the broader geoscience community. Most people would associate access to AVRE with the discovery portal, but there's also now the AuScope Cat Python package that you can use, for instance, in Jupyter notebooks or other Python implementations. And we are in the process of creating a QGIS plugin that you can find and import AVRE data straight into your QGIS, desktop GIS. So to really know what is happening, we are developing quantifiable metrics for the success of these key products, and try to collect more user statistics to get better insights on what people really use and how they're using it, and if they're not using it, what might be happening there. I already said that this is kind of a paradigm shift to AVRE, adding catalogs and data repositories. So we've already implemented a data repository for AuScope that holds data publications from geochemistry now, and we're working with other communities as well to host their data or provide data backup services. We've built a sample catalog where users can register samples that their research is built on. And what will be coming shortly is instrument register that is a list or catalog of all instruments that were co-funded or invested into by AuScope, and a register of research activities. That's new development in current research information systems that lists all the projects that AuScope has co-invested into, and helps make linkages between project activities, the data, publications, samples, and the instruments used in those projects that will help AuScope headquarters to get a better overview of the impact of their investments into research. But all those linkages between all those objects will also help users of AuScope infrastructure find things in the AuScope universe. And this brings me to this last point, which is a bit further along in our agenda for AuScope virtual research environments: search capability. Search, since the beginning of the internet, has been an issue, and there's everything on the internet, you just can't find it. And the same is true for data and other things from AuScope. So this has been ongoing work for all the time. We have a simple text search right now, which we seek to improve. It's currently based on a technology called Elasticsearch, and we recently had a workshop with one of the lead developers of Elasticsearch to help us improve this index technology in our implementation. But the future that we're moving towards is natural language search. So in a natural language search interface, you will be able to ask a question in plain English to then help you find the data and computing resources that you're looking for. So on the right-hand side is a mock-up of what this might look like, so that you can basically then type a sentence into the search box and say search, and it will come up with a list of catalog entries and images, suggesting that this might be what you're looking for. The technology in the background of this is large language models that you will all have heard about, and since this is a little bit into the future, we're still looking at how we might implement this. The development of this technology is very fast at the moment. So if you ask me in a year's time, the implementation might look quite different to what I might be telling you today. But I think this is a really exciting development, because the use of large language models could also help with augmenting metadata in catalogs, and not just helping you find things in the catalogs, but also help you populate catalogs and data and sample descriptions. So in summary, AuScope virtual research environments keep evolving to meet the needs of you as the community for data and data analysis. We are working on keeping AVRE sustainable by keeping pace with technology changes and the changing user requirements. The big shift really has been adding repositories and catalogs for data, samples, instruments, and projects, and adding to that persistent identifiers for those entries, and enabling the cross-linking between those elements. We're working on improving the findability of data through updated interfaces and natural language queries, improve the access to data through the AVRE API and the QGIS plugin, improve the interoperability with other AuScope programs and NCRIS facilities, and support the reuse of data through access to documentation of the context and provenance of data, because without context and provenance, it really is very difficult to make sense of what those data might be and how you could use them. And you might have noticed the clever use of the FAIR acronym in the summary. So we're really committed to implementing the FAIR principles in this context. So thank you.
We have time for a very quick question. Going once, going twice. And at the front.
I guess why was the choice of having a QGIS plugin versus, I guess, other kind of analysis, or like not analysis, but platform, I guess. What drove you to choose a GIS platform to add the plugin?
So when we looked at how much effort it takes to emulate a GIS as an online tool, as we now do with the Discovery portal, we decided that this might not be the best of our resources, that a lot of the spatial analysis using map layers actually happens in GIS. And so we thought it would be better to make it easier to import things from AVRE into a desktop GIS rather than to emulate a GIS on a web platform.
Thank you so much. Great. Well, before we have our next speaker, why don't we do another stretch like we did yesterday? For whomever wants to, please stand up very quickly. Otherwise, we get the sleeps after morning tea. Give it a little shake. Maybe face one wall, maybe face another wall, and move your shoulders around. Because coming back, we've seen him earlier before, but we've got Sia coming back, and I'll get you set up. Sia, here we go. Do you want this one?
Yeah, should be all right. Hello again. So for this talk that was originally supposed to be given by me, I will focus on our first application of Geodop, which is reconstructing the evolution of the Earth's mantle. So to begin with, we know the Earth's mantle is convecting. It works as a heat engine. At the surface, we have the plate tectonics, the lateral movement of the plates, and at the core mantle boundary, we have the outer core, which the whole thing works as a heat engine. Now, because of these convective currents, we know there are forces generated, the surface is uplifted or subsides, where we have, for example, dense material going down, where we have hot material, we have the upwellings. Now, this has been known by theory for so long. We can look at the geological history, and it's just not theory. We can just go to the southern margins of the Australian continent, where we have the Nullarbor Plain, and as the name suggests, we have these vast plain, very flat surfaces that have been formed in marine conditions, so they've been below sea level, and for whatever reason, they have been just uplifted by hundreds of meters all of a sudden. This goes into this narrative of Australia as a tilting continent. So the southern part of Australia is uplifting, the northern part is subsiding. Now, I just go to the earlier discussion this morning about looking at some of these paleo proxies for sea level and looking where the sea level has been, which can be used for future predictions of sea level. Now, I want to remind everyone that all these paleo proxies are, of course, moved by these forces that we just went through. So when we look at, for example, the paleo sea level markers from mid-Pliocene, where we use usually as a marker for where at the end of this century sea level is going to be, we see that all these markers are all over the place. So there is not one prediction of sea level. And of course, this is because all these markers can easily be moved by hundreds of meters at each location. So this shows that it's necessary to replace these cartoonish figures by some dynamic models. Why we know this is a so-called digital twin for the Earth's mantle. We can go to these models, we can correct these proxies, we can just look at them, just, okay, what has been the evolution of the Earth? How can we correct so many of these different processes that are affected by the Earth's mantle? Now let's do that. We're here at present day. We have the wealth of data as demonstrated by some of the other researchers here from data collection of present day. We have the images of the Earth's mantle supported by this data. And then what we can do, you can use the first principle physics, go back in time, and then at that point we have all these observations from geology, we can correct them and so on. Unfortunately, this is not a straightforward process. This has diffusive processes. This is unstable numerically, you cannot solve it. So what we should do then, we can just turn into our optimization techniques. We have the models, we can run them forward in time. We have the observation, we can optimize these models, we can learn from the data, we can optimize the input, and then we will have the so-called digital twins, the optimized models. Now, I'm not going to talk about it, of course. We're going to do that in Geodopt. Instead of all that jargon of just optimization and adjoint and everything, I'm going to show in practice how this method works. So here, imagine this is the past history of the Earth. Here we are present day. We have no knowledge of how the Earth's past looks like. We just have some very wild guesses. At present day, we have images of tomography models. We can use these first principle physics of conservation. We can move forward. We can just come forward in time until we arrive at present day. And this is the part where we have the data. And then we can measure how bad our initial guesses were. So we can measure this misfit, this error in our predictions for present day where we have the data. And of course, some preferences for how this should look like. And then using this, then we can perform these misfit calculation, and we have these surfaces of misfits. Ideally, if our initial guess, if our guesses of the parameters are correct, we would have a very small misfit. But if we are not very good at initial guess, our misfit would be somewhere high above the surface. And at that point, this is where the adjoint method comes to aid us. We can use the gradient information, we can look at the slope of these surfaces, and we can move in the reverse direction of that slope, and we can just find our way from where our initial guess is to where our initial guess is better, and hopefully we do it iteratively, and we would just land somewhere where it's optimized. So that's the whole jargon of optimization. How does it look for building a reference Earth model? Now, what we do, we use a tomography model. You can pick your own model. We're just using a reveal, which is a model full waveform tomography, which we've used very recent advances in full waveform tomography and data that partially has been collected here in Australia. We convert this through thermodynamic models of the mantle to temperature, and we end up with this present-day prediction of temperature for the Earth's mantle, the deviations of temperature. We have this so-called like large low-velocity provinces in the mantle. And this is our data. This is what the present-day prediction of the Earth's mantle should look like. And what I do, I start from, and then, of course, we use all the data coming from plate reconstruction models. Basically, bottom line here, I want to say all the parameters are as good as it could get, and still we want to predict this model. So what I do, I start at 10 million years ago, and I use one of these forward models that assimilate these data for billions of years, 100 millions of years, and I arrive at 10 million years ago, and that is what my prediction for 10 million years ago looks like. Ideally, if I start from that, convect forward, I should be able to reproduce this, okay? That is my basically successful scenario. I do this, and unfortunately, it looks a little bit like that, but it doesn't look like this, okay? We have this formation of hot material at the, underneath Africa, but it's visibly different. Now, I could do the magic of optimization. This works through processes. I measure how bad my, my initial guess is. Through iterations, I can optimize that. That means like when it comes coming lower by orders of magnitude, it means my initial guess is better. How does it look? So this is my, before I start the optimization, these are like one of these models that is out there and people use. This is how it looks like. And after I do 10 optimization iterations, this is what model looks like now. Basically, it says, if you telling me that this is how your present day should look like, I can optimize an initial condition such that you arrive at that. Now, what is the benefit of that? Now, this is your digital twin. You can just use this. This is the present day. You can just go back in time. You can just track down every point in a seismic tomography model. You can say, this is the history of that. This can be linked to this geologic observation, or this shows that this anomaly is not correct because it has this prediction for this geological observation. But also, I can, for example, go look at the forces that are generated around the Australian margin, see what is the prediction of this model for how much the sea level change should be corrected based on those original markers. Yeah, 4 million years ago, 6 million years ago, 10 million years ago. Now, this was a pilot study. Our final goal for this year, this is 10 million years ago, would be to publish GPREM. If you know anything about PREM, you know this is the gold standard of seismic 1D seismic models. We want to publish GPREM, Geodynamic Preliminary Reference Earth Model, and we want to go back 60 million years, so basically a reconstruction for the Cenozoic era. And with that, I want to finish this presentation. Thank you very much.
We've got quite a bit of time for questions. Does anyone have any?
We made it in the end. Nobody fell over. These sloping surfaces are kind of hard to balance on. Really nice presentation, Sia.
Thank you.
This is a really cool idea that you're looking at like present day features to sort of try and invert for what happened in the past. I guess in some ways, if I understand geochemistry properly, which I don't, in fact, I don't even understand it at all. I think geochemists also try to tell us something about like the past states of the Earth. So that's a really cool idea what you're doing, which is quite different. But in doing this modeling to propagate forwards, you have to assume initial and boundary conditions. And those aren't known either.
So the boundary conditions we're inverting for that?
So not only are you inverting for properties, you're inverting for boundary conditions as well.
No, so we can do that in different stages. So what I showed here, I'm assuming and I know the rheological properties, which is the main question mark. Like other parameters are uncertain, but they're very small uncertainty compared to rheology. and the lack of knowledge about initial condition. For these simulations that I showed, I'm assuming I take the profiles that are coming from different data sets, different inversion, and I assume I know what the rheology looks like. I test them with a few things, and I say, okay, let's reconstruct the initial condition. Now, you could, the thing about GEODOPT is that you could just redefine the problem in many different ways. You could, for example, one of the other things that we're doing, the exact geochemical data that geochemists say, these are the pressure and temperatures, we are actually working on that, and our initial results, so this is what Rhodri is working on, shows that we can assimilate those as well. So not only a present day, we can go back in time and simulate temperature. Yes, there are uncertainties, but that is ultimately the best you could do in order to do that. The further we go back in time, obviously, the less certain things will become. But already for these reconstructions, for example, for the Cenozoic, there are so many fundamental questions. For example, sea level contribution we can already answer that. So for these problems, just to answer you shortly, I assume rheology is known, and I invert for initial condition. You can reformulate that as whatever proxies are present there you have, plate motion, dynamic topography, like up and down, and you can invert for present-day rheology. You can answer, you can ask the question in many different ways until you just start converge to a solution.
Cool, very nice. I'll follow up with you afterwards.
We have enough time for one more question. Was one in the middle? I'm playing favorites. No, we're going at the back. Great, sorry.
Hi, Sia. Really nice talk. I got a theoretical question, I guess. So when you're going back in time, you're assuming a closed system, in a way.
You mean close to outer core and the atmosphere? Is that what you mean by closed? Yeah.
Well, to give you an example, say if you have a massive impact and it causes massive mantle decompression, and there's been lots of models in the early Earth. I know obviously you're not modeling that far back, but just an example. The model would not be able to take it. Would it be able to take into account those kind of external, sudden, big variations that then could have massive knock-on effects, like a butterfly effect?
I hope one day our models are so good that we could start thinking about these things. Currently, we're so in unknown territories that I think this is the first time that ever somebody's spoken to me about that.
Sorry.
But no, that's very interesting question. So in terms of like the importance of that, obviously, the further we go back in time, that becomes more important. For now, these models, theoretically, you cannot also go infinitely back in time because information diffuse, and there is certain time that you can look at, for example, present day, and you say that is even related to past because then information diffuses, and then you become basically insensitive to anything that you predict at present day. So yeah. But it's an interesting question. But the typical thing that people do, they use parameterizations of, you say there is an external impact. What force should I put in my model so that it will be representing that external impact, which is a completely doable thing. But then, you could do that, but it's too early to think about those things.
Sia, thank you very much. I think there are a couple more questions, but we'll grab Sia during lunch. I hope that's okay. We have one more person before we do go for lunch, and we have Will Scott, who is a researcher in polar science, numerical modelling, oceanography, and geophysics at the Australian National University. I'll give you this one. I'll get you set up over here, because the computer is doing stuff. Let's ignore what's going on in the screen. There we go. Love it.
Thanks, everyone. My name's Will. I'm a postdoc at ANU, working with the GeoDOPT team. I'm going to be talking a bit about glacial isostatic adjustment and our progress on that, and talk a bit about sea level modeling into the past. So I thought I'd start with this slide. So I'm sure you've seen it before, but this is just showing that we're approaching about 1.5 degrees of warming since pre-industrial levels. And the polar regions are some of the most rapidly changing on the planet. So this is a picture of the change of ice thickness, the rate of ice thickness in Greenland and Antarctica. And you can see around the coasts that we're having big changes in the thickness, and that's now starting to contribute towards sea level rise. So this is, again, a famous picture, and there's lots of uncertainty, especially in the Antarctic projections. But if we take the sort of the median projection of the business as usual scenario, we're looking about 74 centimeters by 2100. And I've got another picture of an airport. So this one's in Cairns, but if you do sort of a naive calculation and put some water on top of the high tide, you can see that that's going to wipe out a lot of infrastructure in Cairns. But this is really the case across the whole of the east coast of Australia. In Tuvalu is another example where the series of atolls they're very low lying. So Tuvalu's highest point is about 4.6 meters above sea level. So any change on the order of a meter is a massive impact on these islands. And so how do we observe sea level change? So one of the obvious ones is tide gauges. So this picture's from New York, just showing a tide gauge at New York. You can see the Statue of Liberty in the background. The other one is satellites. So we've got a wealth of information now coming from satellite data. And the team at CSIRO have been part of the people making sure that we're fitting the sea level budget over the last 100 years. So as a sort of ballpark estimate, we've got about 3.4 millimeters of sea level change per year in the last 30 years. So if we now just sort of zoom into New York, you can see that once you do the conversion to some more normal years, it's about 3.8 millimeters per year. So far this all sort of makes sense. But maybe if you've seen this talk before, you might know what's coming. But if you look in Canada, we've actually got a sea level fall of 10 millimeters per year. So what's going on? And again, if you look across the continent of North America, we've got this gradient in the sea level change rate currently going on. So why is sea level not uniform around the world? And part of the thing, if you sort of haven't seen this before, the key thing to take away is sea level is not quite as simple as filling a bathtub. It's a very good approximation, but in polar latitudes, it's a bit different. Part of that is to do with gravity. So the ice sheets are very big, so they're affecting the geoid. So if you remove ice, then you change the slope of the geoid, and it means that when you move water from the ice into the ocean, you're going to relatively increase sea level in the far field. So sea level rises a little bit more in the other side of the hemisphere to the ice. The other part is evolving surface loads. So because the mantle is able to deform and the ice sheets are very big, when we remove the ice, the mantle's going to rebound and push back up. So when we're in the near field, so when we're close to where the ice sheets used to be, we actually see a sea level fall because the ground's rebounding. So the key process that controls this is viscoelasticity. So you might have maybe seen this famous experiment in Queensland where they have some tar, and you can go and look at it online and watch as the tar is dropping very slowly. And obviously this is the sort of lots of processes on the Earth, or lots of materials on Earth. There are these, you can think about rheology or how things flow and deform on different timescales. So there's elastic motion, that's like seismic waves, or instantaneous changes where everything's just shaking and vibrating. And then we've also got a slower flow, so viscous flow, which is like a fluid, and that's generally to do with grains sliding past each other. So quickly just looking at some elastic motions. So this is an output from a GIA code where you can see the sea level change if you just melt all the mountain glaciers. So this is this gravitational effect where everything's been normalized, but you see that if you look in Australia and the Pacific, there's actually a 10 to 20% increase in sea level. So we can start to measure some of these things from satellites. So it's part of the budget of sea level, and these things are often referred to as fingerprints. And this is the instantaneous emotion when you melt glaciers. A similar effect happens in Greenland. So because Greenland's the other side of the world to Australia, we tend to get, again, like a 5 to 15% change just from these modern melting in Greenland from any melt there. So now let's talk a bit about the longer time scale, the viscous part. So we're going to talk about the changes in ice thickness from the last glacial maximum. So this is a map looking at some reconstructions of what we think the ice used to look like in the past. So about 20,000 years ago, there were much bigger ice sheets in the northern hemisphere. So over northern Europe, over Scandinavia, and also over North America. And one of the sort of the key regions of the world where people first were thinking about these problems was in Scandinavia. So if you go there now and you look, you have there's a lot of GNSS stations, you can very easily measure this uplift. But it's also got a slightly longer story where this rock is called the Celsius rock. So the Celsius, who came up with the temperature scale, he was interested in trying to understand why fishing villages, it was becoming harder and harder for boats to go up the rivers because sea level seemed to be falling. And he had the idea to draw a line on the rock. So this is quite an interesting scale. Like on a human time scale, you can see that in over a number of generations, there's a few meters change in sea level just from this process of there being more ice in the past. The other famous examples are the big raised terraces in northern Canada. So you can see that basically as you have storms, they're marking the shorelines. And as the land is rebounding, you can see all these paleo shorelines from space. So hopefully now this makes a bit more sense about what was going on before. In red, we have the sea level fall because we have the uplift caused by the isostatic rebound. You can see that the blue region is where the isostatic, the fall bulge is collapsing. So that's the slightly more increase around Boston and New York. And then because that's actually creating space for the rest of the ocean, there's a bit of a sea level or fall around in the Pacific. So yeah, that was explaining that. So okay, so what's the knowledge gap? Why are we here and why are we talking about this? To reconstruct one of these maps, it's really, like we've been talking about, it's an inverse problem. We don't really know what the ice used to look like in the past. And one of the sort of the key parameters that's controlling this response is the viscosity. So Kurt Lambeck's group at ANU is famous for developing sea level models to try and predict what the ice sheet used to look like in the past. And that was relying on making assumptions about the radial profile of viscosity in the Earth. So that's a very good, and basically showing that there's like a lithospheric structure. We have some mostly elastic motion in near the top part of the mantle, and then we can try and discretize the viscosity with depth. But we know from seismic tomography and geodynamics that really there are very, very big changes in viscosity. So orders of magnitude changes in viscosity. This is a map that's coming from seismic tomography to temperature to viscosity conversions in Antarctica. So you can maybe see the outline of the Antarctic Peninsula. But you can see that there's very low viscosity predicted in this old subduction zone setting compared to the cratonic part of the mantle in the east of the continent. So if these processes, because it's such an order of magnitude change in the viscosity, that has quite a big impact on GI simulations. So if we want to simulate these processes, people have been developing larger three-dimensional numerical models of this. And to do that, they generally rely on grid-based schemes. The problem is, though, it's this sort of disconnect with doing an inversion where we don't really know what the inputs are. We don't really know the ice history very well, and we don't really know what the viscosity is. So, but we've got these very slow models that then becomes much harder to do an inversion process. So that's, as Sia's sort of been talking about, the key idea really with Geodopt is that we have this ability to calculate a gradient through a model. So it's about trying to speed up an inversion process. So to try and make an inversion using a three-dimensional model tractable. So I've got just now some synthetic examples in the next few minutes just to give you a sense of what we're trying to do. So this is a cut through the mantle, just in a synthetic domain. So we've got some blobs of different viscosity. So some low viscosity pretending to be near West Antarctica in the bottom. Some of these LSVP type features in the core mantle boundary, and then some higher viscosity blobs in the north, which is to represent some slabs and some cratons. And if we put some ice sheets on, so just some synthetic ice sheets, like a big one near the south and another one offset from the north, we can run the simulation forward, and you can see that it's slowly evolving towards a state of isostatic equilibrium. So by the time it's at 10,000 years, most of the deformations occurred, but it's still evolving very slowly. So this is just to zoom in at 3,000 years. So this was this picture about here. So if we look at a difference between a model that has the viscosity structure, or this lateral viscosity structure, and one that doesn't, you get this sort of graph. So this is the surface deformation in terms of displacement and velocity. So you can see that the peaks are generally where the ice sheets are. So you can see that the biggest differences are where you have the ice sheets and the low viscosity regions. So basically, the low viscosity is allowing you to have faster deformation, and the radial profile is trying to catch up. And it's sort of the reverse in the location with the smaller ice sheet, where there's higher viscosity in the lateral case. And so we can do like a test just to see if this is going to work, to get a sense of how this is going to work, by using the results from the lateral case and pretending that's really what the Earth looks like, and looking at the surface deformation to try and see, can we tell something about the viscosity structure in the mantle based on surface observations through time. So these are some panel plots just showing, so if we start from this, we don't know what the viscosity structure is, we just have this radial profile. In the middle is just showing because we know what the true model is, this is just showing you the misfit to get a sense of where the model's going wrong. And then this on the right is a sensitivity kernel. So this is a bit like when people look at seismic tomography or they're looking at the adjoint kernels. This is really just showing you the gradient of the surface misfit with respect to the viscosity field. So it's plotted in log space, but the red region that's corresponding to where the low viscosity is saying that the gradient's always going to point uphill. So it's saying that if you want to increase the viscosity in that region, that's going to increase the misfit. So basically, everywhere you see red, it should be trying to reduce the viscosity. So we can run this forward. So this is sort of an iterative process. We use the gradient to try and update what we think the viscosity looks like. So now, after 10 iterations, we've recovered this low viscosity blob in the near the southern part of the domain, and we're starting to see some structure in the lower mantle. And you can see that on the right, the sensitivity kernel has changed a lot. So now you're starting to see a lot more structure in the deep mantle. And that's sort of showing this iterative process. So as we get closer to the real solution, our sensitivity patterns are going to change. And so we can keep doing this for 50, for 100. And because this is a synthetic example, we can run it for a lot of iterations. And this is showing that by 100 iterations, we've actually been able to capture pretty well the original structure of the model. We can do a very similar thing. Oh, and this is just showing the misfit through time. So in the synthetic case, you can reduce the misfit by many orders of magnitude. So we can do a very similar thing with the ice. So if we say we start from a model where we don't know what the ice used to look like, there's no deformation, so there's obviously a big misfit. The inner ring is showing the sensitivity kernel again. So in this case, blue means that if we increase the ice thickness, that's going to decrease the misfit. So it's saying that really we want to put some more ice in the southern hemisphere, and that massively overshoots. But we get a new prediction of what the surface displacement is. So there's a new misfit. It recalculates, recalibrates, and says, oh, we need to decrease the amount of ice that we just put there. So if we run this now for a few iterations, for 3, for 4, for 5, you can see that it's starting to recreate the spatial pattern. And by the time you get to 10 and to 20, we've been able to reproduce again we've been able to reproduce the structure in this synthetic case of the ice thickness. So there's a short story here about just if you use the wrong viscosity structure, what kind of biases are you introducing into the model? So the red is saying that we didn't know what the ice thickness was, but we used this wrong radial profile case without the lateral viscosity structure. And that's introducing some bias, basically in the regions where we know there's some lateral variations in the viscosity. And you also you're not able to reduce the misfit as much. I guess the other question in this case is, can you reconstruct both at the same time? And the answer is you can. So what happens is really the biggest sensitivities, if you make sure you weight the surface sensitivity, because the ice thickness is very thin, because the ice is really on the surface, you have to be a little bit careful with how you weight the sensitivities. But once you're correct for that, what happens is the first few iterations are really concentrating on making sure we get some structure in the ice model. And then by the time we've got to 10 iterations, we've reproduced where the ice thickness is. So it's really just a question of trying to invert for viscosity again. So I think that's the key idea, is that really when we're going to run bigger models, we're probably in the range of 10 to 15 iterations. So we can probably, if we only knew the surface observations and had no idea from tomography about viscosity, we would probably only ever be recovering parts of the viscosity structure that are close to the ice sheet dynamics. And that's just again showing the misfit reducing through time. So I just wanted to finish here. So just to remind you, our outlook is we're trying to reconstruct maps of what the ice used to look like in the past. based on lateral variations in viscosity that we know exist from geodynamics and tomography. And the key thing is that's trying to improve our estimates of current sea level change into the future. So thanks very much. Thank you.
How good. Thank you for that. Well, we will save questions for lunchtime. So if you've got any questions for Will, please hit him up during lunch, which we'll be going to imminently. Before we do, though, I've got Tim who'll be joining us before we go for lunch. Here we go.
Thanks, Dave. Thanks, Will. Thanks, everyone, for those talks. I just wanted to quickly say a couple of things. One is SEMA wants you all to vote for your favorite video. If you haven't watched them yet, you've got time to watch them over lunch. We'll put the QR code up on the screen in here so you can pop in and use the QR code to, it's not there yet, I'll put it up in a sec, to find those videos and look at them. I voted this morning. Don't worry when you get told you got the answer wrong. That's a little quirk with the software. So that was one thing. There was one other thing. It seemed really important when I asked Dave if I could grab the microphone. I know what it was. So we're going to go to lunch now. We've got 3 more talks, and then we've got an interactive session. I just wanted to say, so earlier we had this little interactive thing that we did where we offered you $10 million. We don't really have $10 million to offer you. But the interactive session this afternoon is a bit more sophisticated. So we actually are going to get you to pose something that we are going to spend real money on. So I just want you to know, if you're thinking of skiving off or sneaking out before we get to that session, we are going to actually put $20,000 or thereabouts on the table to help support something that an idea that comes out of this conversation we have this afternoon. So we do want you to be involved in that. So get your thinking caps on. We'll give you more information about what we're going to do after the next 3 talks. But it's going to be an exciting opportunity to really build something, because often we ask you to give us ideas and you don't see those turning into something. We're actually committing some funds to work with you to try to build something out of the conversations we have this afternoon. So enjoy your lunch and get creative.
Yeah, let's go for lunch. Thank you so much, guys. We'll put the QR code here so you can come in during lunch.